Right now I'm going to explain the process for integration with partial fractions. Actually, before I do that, I want to show you guys one thing, and that is this integral here, 2 divided by x plus 1 times dx. So if your integral in the denominator is a linear factor, which is like an x plus 1, or x has to be to the first power, then by u substitution, okay, so if we let u equal x plus 1, then our du is going to just be equivalent to dx. And then we could substitute, we could do a u substitution, and this integral is going to become 2 times 1 over u times du. And the integral of this part in the parentheses is just the ln, the natural log of u, and then of course it's going to be times 2. Okay, so basically anytime you have this linear factor here in your denominator, the integral is going to work out to be a natural log of that term. So this is kind of an introduction to partial fractions, because what we're going to do with partial fractions is break down bigger polynomials into the sum of some of these smaller fractions that have linear terms. So our answers are going to have a bunch of natural logs in them, but that's okay because it's still going to be the easiest way to approach the problem. So I will now give you a pretty good example of exactly what I'm talking about. And we'll start out with this one. X squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x all times dx. Okay, if you notice, u substitution in this case is not going to work. Integration by parts is not going to work. Trig substitution not going to work. Okay, so what are we going to do? We're going to break this down into some smaller fractions. The way you might know that is by noticing that this denominator can be factored algebraically. So the bottom of this fraction is a third degree polynomial. So we're going to take it over here to the side. And we're going to try and factor it. So if you've forgotten the steps of factoring, the first thing that you always do is factor out the greatest common factor. So what do all three of these terms have in common? Well, they have an x, right? So we're going to factor out an x. Then we're going to get 2x squared plus 3x minus 2. And then we're going to apply product sum. And if I'm not mistaken, the x squared term factors into 2x minus 1 and x plus 2. And then of course to check that you could FOIL those two terms together. However, I think I've done it right. So that's kind of broadly the first step here, is to factor the denominator of our integral. Okay, so we have integral x squared plus 2x minus 1 over x times 2x minus 1 times x plus 2 all times dx. Okay, I'm going to erase some of this stuff now, so we don't need it anymore. Okay, now that our denominator has been factored, again, this is kind of an algebra trick, probably from Algebra 2 or maybe from a trigonometry class. I can't actually remember right now specifically when this lesson was taught, but if we take this fraction here, we should probably be able to know or remember, or if not, I'm telling you now, that this fraction could be broken down potentially into the sum of 3 different fractions. Now it may be difficult for you to tell what is A, what is B, and what is C, but theoretically, if you have 3 factors in your denominator of a fraction, then you could potentially split that fraction into 3 different fractions with 3 different denominators. And I guess maybe I'll make a lesson on partial fractions only if you're curious about why this works. But if you have some algebraic intuition, you might be able to see why this would work. Anyways, the way that you solve this at this point is you multiply absolutely everything in the equation. So I mean this term, this term, this term, and this term. So we're multiplying all 4 pieces by the total denominator. So we're going to multiply everything by x, we're multiplying everything by 2x minus 1, and we're multiplying everything by x plus 1 on both sides. Okay, so what is that going to do? Well, for this piece, it's going to cancel out all 3 of the pieces of the denominator, right? So on that side, we're just going to be left with x squared plus 2x minus 1. And then when we multiply this stuff by a, the x's cancel out, and we'll be left with a times a 2x minus 1 and an x plus 1. And then when we multiply all this stuff by the b term, the 2x minus 1 cancels out, and we will be left with b times x plus 1. And then finally, when we multiply this by the c term, the x plus 1's get canceled out, and we're left with c times x times 2x minus 1. Okay, so this doesn't seem much simpler, but in fact it is. This is going to help us out tremendously. Okay, so this long equation that we have here, we're still trying to figure out what is A, what is B, what is C. And the way that we're going to do that is we're going to remember that this statement that we have here should be true for all values of x. And basically what that means is we can plug in anything for x and the equation would still hold. So that's what we're going to do, except I'm going to strategically pick some values of x to make our lives a little easier. But you should be able to plug in absolutely any value of x into this equation and it will work. Okay, so I'm going to pick, what am I going to pick? First I'm going to pick x equals 0, so I'm going to try x equals 0. And we're going to get 0 plus negative 1 is equal to a times negative 1 times 1 plus b times 0 plus c times 0. Okay, so we find out that negative 1 is equal to negative 1 times a. So I think that means that a must be equal to 1. And I'm going to write that down. And I'm now going to plug in a different value of x. Right? Again, this should hold for all values of x. I chose 0 strategically because that would make this 0 and make this 0, which leaves us with only the a coefficient. So that was extremely helpful to choose x equals 0. Okay, the next thing that I'm going to try is x equals negative 1. Again, I chose this strategically. If we plug in negative 1, we're going to get 0 here. We're going to get 0 here. So that's going to leave us with only the c coefficient remaining, which will be helpful, right? Okay, so negative 1 squared plus 2 times negative 1 minus 1 is equal to a times 2 times negative 1 minus 1, that's negative 3, times 0, plus b times negative 1 times 0, plus c times negative 1 times negative 3. So we have no a's, we have no b's, and we have 3 times c equals, I think this is negative 3? No, it's negative 2. 1 minus 2 is negative 1, minus 1 is negative 2. Okay, so c is going to be negative 2/3. It's a fraction, but that's alright. Okay, the last value of x I'm going to try is 1/2. And the 1/2, when plugged into this piece and this piece, is going to give us a 0, and we should be left with only some b coefficient left. So that's good. We don't know what b is, so try 1/2. Unfortunately, it's not as easy to plug in fractions. So 1/2 squared is 1/4 plus 2 times 1/2 minus 1 equals a times 0 plus b times 1/2 times 3/2 plus c times 0. Okay, so it looks like we're just going to get 1/4 equals b times 3/4. And if we divide by 3/4 or multiply by 4/3, we find out b should be 1/3. Okay. I'm now going to erase this equation here at the bottom. I probably should have left the original fractional decomposition, but basically this polynomial here is going to turn into a over x plus b over 2x minus 1 plus c over x plus 2, and then the whole thing is being integrated with respect to dx. Okay, so we just reduced our one very complicated integral into, well, ultimately this is going to be 3 less complicated integrals. Oh, I forgot to plug in c. C is negative 2/3. Okay, so what this is going to do is turn our one integral into 3. So we have 1 over x times dx plus integral of 1/3 over 2x minus 1 dx plus integral negative 2/3 over x plus 2 times dx. Again, basically, well, okay, so this first one here just turns into ln of absolute value of x right off the bat. This one, you'll have to do a u substitution because u is equal to 2x minus 1, which means du is 2 times dx, which means the dx actually becomes 1/2 of du. And then you get 1/3 times 1/2 times ln of 2x minus 1. I better just write this down here. Okay, ln absolute value of x plus 1/3 times 1/2 times ln absolute value 2x minus 1. And then this one is going to be plus this one here, plus negative 2/3 ln absolute value x plus 2. Again, for that one, you should do a u substitution, but du and dx are equivalent, so you can, or if you kind of know what you're doing, you can kind of just skip that step. And this is going to be plus some arbitrary constant. I might even say plus this negative 2/3 here is just going to be a subtraction. And this 1/3 times 1/2 is really going to be 1/6. And then there's your answer. Okay, so I think I'll do one more example. Okay, so I paused the recording for a moment, collected my thoughts. I came up with a new example here. This will be example 2. I think I might actually do more than 2 examples this time, because the decomposition into partial fractions is a little tricky. So one thing you might notice about this example is that the degree of the top is larger than the degree of the bottom. So we have an x to the 4th on top, right here, and we have an x cubed here on the bottom. So actually what that means is, well, we're going to have to do long division first. So we're going to have to take x to the 4th minus 2x squared plus 4x plus 1 and divide it by this one. So we're going to get an x Okay, so it appears that we have a remainder of 4x here. There's nothing we can really do about that except for this. So we'll say plus 4x over the divisor. Okay, so we have simplified our integral somewhat. even x plus 1 plus okay, so we still have a pretty gnarly denominator here, and we gotta do something about that. That x cubed minus x squared minus x plus 1. Okay, since we're doing partial fractions, we probably want to make sure that, or, well, right, we want to check and see if that denominator is factorable. And I have chosen this denominator because it is, in fact, factorable. So we'll go over here, and we'll try and factor it. I'm noticing we could probably do factoring by grouping. And we could factor out an x squared from the first two and a minus 1 from the second two, and then we'll get x squared minus 1 times x minus 1, and this can be factored again, so that's x plus 1, x minus 1, x minus 1. That could be potentially rewritten as x plus 1 times x minus 1 twice. Okay, and here we have a new special problem. So if any of your factors have a multiplicity greater than 1, such as our x minus 1 factor here, something new is going to happen. Something new compared to example 1. So I'm going to rewrite, what am I going to do? No, I'm going to take this little 4x piece here, and I'm going to start decomposing it with our letters A, B, C, etc. Okay, so this could be, oh, well, we could go ahead and write our factors here. This is going to be 4x over x plus 1 times x minus 1 squared. Okay, so basically, the new thing is this could be the composition of a over x plus 1 and a b over x minus 1 and a c over x minus 1 squared. So in the case where your multiplicity is greater than 1, you need to include all possible powers of that factor. So here we have x minus 1 to the first and x minus 1 squared. We need both of those. It's possible that one of them, like b or c, could be 0, but we can't assume that. So we need to include the option to have all three of these factors available. Okay, so just like last time, we're going to multiply absolutely everything in this giant equation by the entire denominator. So x plus 1 and x minus 1 squared on both sides. This piece just works out to be 4x, and that's going to be a times x minus 1 squared plus b x minus 1 x plus 1, and then c times x plus 1. Again, this statement that I just wrote should be true for all values of x. So we can just plug in some things strategically and find out what a, b, and c are. So the first thing I'm going to do is try, I guess, x equals 1, right? That would eliminate a and b. So we'll get 4 times 1 equals a times 0 plus b times 0 plus 2 times c. So if 2c is equal to 4, that means c must be equal to 2. Okay. I think we should probably also try -1. So we're going to get -4 equals a times -1 minus 1 is -2 squared is 4 plus b times 0 plus c times 0. So it looks like a has to be -1. Okay, so at this point we're out of strategic options, unfortunately. So I'm just going to pick a random x value. Not totally random. I'm just going to try x equals 2. And I could have done -2, I could have done 3 or 4. I'm just picking like the smallest positive value that we haven't already tried. Anyways. Oh, and also I'm going to plug in a equals -1 and c equals 2, because that would leave us with only the b coefficient unknown, and that's basically what we're trying to find. So we get 8 equals a, which is -1, times 2 minus 1 squared is 1, plus b times 1 times 3 plus c times 3. Oh, I'm sorry. C should be 2. Okay, so we get 8 equals -1 plus 3b plus 6. Well, we can add 1, we can subtract 6. Add 1 and subtract 6. That's going to be 3b equals 3. So that tells me b must be equal to 1. Okay, so that wasn't too hard. So now we're going to come back up here to our integral, which is already pretty complicated. And we're going to rewrite it. Okay, so this x plus 1 stays the same. And remember, this 4x over the x cubed, we just broke it down into 3 easier fractions. A over x plus 1, b over x minus 1, c over x minus 1 squared. Okay, so that's going to give us -1 over x plus 1, 1 over x minus 1, and 2 over x minus 1 squared times the dx again. Okay, so does this look easier? It should look easier. It looks longer, but it's actually going to be easier. Okay, so the integral of x is 1/2 x squared. The integral of 1 is x. The integral of -1 over x plus 1 is just -1 times the ln of x plus 1. The integral of this piece is just 1 times the ln of x minus 1. And finally, this piece requires a u substitution. So 2 over x minus 1 squared times dx. We're going to let u equal x minus 1. In that case, du would be equivalent to dx. So we could rewrite this as 2 over u squared times du. Or, even better, 2 times u to -2 times du. And that integral works out to be I think it's just -2 u to the negative 1, or negative 2 over u. At that point, you plug u back in. So this is going to be negative 2 divided by u, which is actually x minus 1, and then plus some constant. There's your answer. Okay, I think I might do one more example, because there seems to be one more case that we have not addressed. So I will do that in just a moment. Let me clear all this stuff out. Okay, so I think I've decided that the next scenario should probably be its own video because it's quite complex, but I am going to show you an example so you know what to look for. The example would look like this: 2x squared minus x plus 4 over a factor that might look like this. So basically what is different about this than the last example is that this piece right here, this x squared plus 4, cannot be factored. Into two linear terms. So basically you're stuck with the factor x squared plus 4. And when you have a fraction with x squared plus 4 on the bottom, you have to approach it in a different way, because the integral of this requires either a u substitution if possible or an inverse tangent. In other words, it's not going to work out to be just a simple natural log of denominator. So if you have anything other than a first power of x on the bottom, you need to take a different approach. And since this x squared plus 4 cannot be factored, we're going to have to take a new approach. I'll go ahead and cover that in the next video, because I think this video is long enough, it's covered enough, and I think this third scenario is less common, so at least the first two examples will get you somewhere, and we'll talk about this one soon. As always, let me know if you have any questions.